Part 2 of your lesson starts with a warm-up. So I'm going to ask you to pause your video, try this question, and then hit play when you are ready. All right, here is the answer for the warm-up question. I have all my work shown. So you're going to hit pause, check your work real quick, and then hit play when you're ready to move on. So the next thing we're going to learn how to do is we're going to learn how to take a power series or a geometric series, and we're going to learn how to differentiate and integrate such things, which sounds like it's going to be complicated. I can assure you it is not. Remember that this is something that people do when they can't integrate or differentiate a certain item due to complication. So this is a simpler process than anything we've seen thus far. It is actually the process we're going to use is called term by term differentiation and or integration. So that literally means you will take one term at a time and differentiate or integrate each term as you go. Okay, let me just show you some examples to explain what I mean. Okay, not here. So for the Bessel function, this one is done actually without term by term integration. Let me just come back to that one later. It's a little bit confusing. Let's do one that's term by term. Okay, express 1 over 1 minus x squared as a power series by differentiating equation 1. So they're referring to something from back earlier in the notes. I will pull that for you and have you write down equation 1 is 1 over 1 minus x. Okay, it says express 1 over 1 minus x squared as a power series by differentiating equation 1. So what they're implying is that the derivative of 1 over 1 minus x squared is equal to this, okay? So we're going to start by saying, let's see, is the derivative of this thing 1 over 1 minus x equal to 1 over 1 minus x quantity squared? That's the question. Okay. Possibly. Should we do the math real quick? Let's see what happens. So how do we find 1 over 1 minus x? Let's write it as 1 minus x to the negative 1 power is what it would be, right? If we take the derivative, we would do mama baby times the derivative of baby, which would be negative 1. And if we move everything around, you would get a positive 1 on the top, 1 over 1 minus x squared. Look at that, it does work. Okay, so here's the situation. I want to write this as a power series. I can't the way that it's written because it's got an x squared, which makes it impossible to write it like a over 1 minus r. So instead, we're going to use a differentiation or derivative trick, okay? So we're going to recognize that 1 over 1 minus x is the antiderivative of 1 over 1 minus x squared. So we're going to kind of work in steps. So let's start with this, and we're going to write this as a series. So let's see, A, it's already right in the correct format. So A is 1, R is x to the power of n. Okay, that was pretty easy. And we're saying that if we take the derivative of this, we get this, right? If we take the derivative of this, we get this. Well, the series I just wrote that represents 1 over 1 minus x. If I take the derivative of that, that's the theory, then I'm going to get the 1 over 1 minus x squared series. Okay, how do you take the derivative of this? Well, it's the same way you take the derivative of anything else. Okay, watch me. You take the power, you move the power to the front, and you subtract 1 from the power. Right? Isn't that how that works? Take the power to the front, subtract 1 from the power. Now, when you take a derivative, don't you typically lose a term? And when I say lose a term, remember how like x to the n represents 1 plus x squared plus x to the third and so forth? Well, what's the derivative of 1? It's 0, right? So you would end up with 1 less term than what you started with. So when you write your series setup, you're going to put n equals 1 here instead of 0 because you took a derivative. So you now have 1 less term than what you began with. Okay, what you have currently right here is representative of 1 over 1 minus x squared. So you answered the question. You could also take it one step further. This is not always required. You could take it one step further, and you know how like we had to change the bottom to n equals 1 because we took a derivative? You could change it back to a 0 by manipulating your question a bit. So basically you want to add a term. So you would need to add 1 to all your n values. And that would make it n plus 1 times x to the n. So either of these answers would be perfectly acceptable. I know that's tricky, so stay with me. I'm going to show you some more examples to help you through. Find a power series representation for ln of 1 minus x. Oh, and its radius of convergence. Convergence got cut off there. All right, find one. We don't have anything to go off of. So we're going to start playing around with, obviously this doesn't look like a over 1 minus r, right? Doesn't even look close to that. So let's think about how we could make it a over 1 minus r in that format. Well, what if we took the derivative? Wouldn't the derivative of ln be something kind of like that? What's the derivative of ln of 1 minus x? It would be 1 over 1 minus x times derivative of baby, which would be -1. So I'll just make a -1 on the top. Now, is this something we could write a series for? This is, because this is in the format a over 1 minus r. Okay? So now we need to keep in mind the derivative of what I need a series for is something I can write in terms of a series. So let's do that first, and then we'll work backwards to get back to the ln thing, okay? So -1 over 1 minus x. What does that look like as a series? Well, the first term is -1, and the ratio is x to the power of n, okay? But this represents the derivative of what I need. I need ln, and I have its derivative right now. So what you need to do is take the antiderivative to get back to ln, okay? So we're going to take the antiderivative of this 1 over 1 minus x thing, and that's going to give us a series that represents ln, okay? Now, taking an antiderivative of a series is not that hard. It still follows the same kind of procedure as a regular antiderivative, okay? So you're going to, I have a -1, I'm going to add 1 to my power and divide by the power. So add 1 to n and divide by n plus 1. And what do we always put at the end of a series? Or sorry, end of an antiderivative, plus c, okay? Now in this one, we do have to find the value of c. Here's how we'll do that. This answer right now, because I took the antiderivative, should be representative of the series we were asked to write, which is ln of 1 minus x. So right now, these two things are equal to one another. Our answer just is not complete because we don't have the value of c. That's not known yet. Okay? So what we'll do is we will take 0 and we will plug 0 in for x, and that's going to help us find the value of c. Okay? So you're going to plug in x equals 0 to find c. All right, so let's see what happens. Ln of 1 minus 0. All this series stuff over here. Okay, all of this stuff on the right, 0 to the power of n would just be 0. So all of this is going to go away, isn't it? It doesn't matter. The series won't really change because you're doing 0 divided by everything. So you end up with ln of 1 is equal to c, and ln of 1 is equal to 0. So c is 0 in this problem, which means that you now have an answer. Ln of 1 minus x is equal to the antiderivative that we created, which was x to the n plus 1 over n plus 1, and I forgot a negative, -1. There we go. Plus 0, which I'm not going to write plus 0. All right, part 1 is done. It did also say find the radius of convergence. So you have to do the ratio test to find the radius of convergence. Remember, if you're just finding the radius of convergence, you do not have to test the endpoints, because the radius doesn't really matter whether the endpoints are included or not. Okay, I think I got everything set up correctly. I'm going to go ahead and do my outer inner and my decomposing step. My -1s are going to go away because of the absolute value. All right, I think I got everything. X to the n's are going to cancel, and then you can cancel one of the x's. So let's see what we, I didn't want red. Let's see what we end up with here. The limit, we're doing n plus 1 over n plus 2, and I just have an x, I think, left over. What's the limit going to be? The limit's going to just be 1, right? So I just have the absolute value of x has to be less than 1, which means that my radius will be 1. That was a tough one. Okay, 2 more. Find a power series representation for tangent, inverse tangent. This is, again, it's like a puzzle, okay? Obviously, you cannot write inverse tangent as a power series because it doesn't look like anything like a over 1 minus r, not even close. So think about what you know about tangent. Does inverse tangent's derivative or antiderivative look like the setup that we need? Well, what is the derivative of inverse tangent? That would be something you probably have to dig back and find. The derivative of inverse tangent is 1 over 1 plus x squared. Is that closer to the format we're looking for? Yes. So we're going to work with this. Okay, so we're going to find a series to represent 1 over 1 plus x squared, and then we'll go backwards to find the series for inverse tan. Okay, so let's start with 1 over 1 plus x squared. How can I make that look like a over 1 minus r? Well, pretty easy. All I need is to make it 1 minus negative x squared. And I can write my series. So the first term is 1, which means we just have negative x yeah, I guess I could write it to the, no, I can't. Hold on. I'm talking to myself. It would be negative x squared to the n. There we go. And then I may want to split it up and put the negative separate. So let's call it negative 1 to the n x to the 2n. That's what I was trying to say. Okay. The derivative of tangent gave us this. So to go backwards, I need to take the antiderivative. So the antiderivative of 1 over 1 plus x squared will equal inverse tangent. Well, this series we just wrote represents 1 over 1 plus x squared. So we need to antiderive the series we just wrote. And that's going to take us back to what we want. All right, remember the rules for anti-deriving something. The rule is you add 1 to the power. Now remember, this is a constant, so it is unaffected. Let me get this ready. You add 1 to the power. So it would be x to the 2n plus 1, and you divide by the power, which is 2n plus 1. Plus c, don't forget plus c. And then we can write down our conclusion. So this is supposed to be the inverse tangent is equal to the series that we, I forgot the n, the n in here, the series that we just wrote. Okay. Last time we also wrote, or we also found the power or the value of c. This time I'm just going to leave it like this. We'll have to read directions to see whether they want you to find that value or not. Last one. Express 1 over 1 plus x to the 7th, the antiderivative of it as a power series. Okay, so we're going to antiderive 1 over 1 plus x to the 7th. Again, this would be something that is actually impossible to do with what we currently know about antiderivatives, which is why we're going to instead look at it as a series, and we're going to antiderive the series, because that seems to be a lot easier than antideriving with partial fractions. So what would this look like as a series? Well, the first term, oh, whoopsie, I got to rewrite one thing. It would be 1 over 1 minus negative x to the 7th, right, to be in the right format. The first term would be 1, and then it would be negative x to the 7th to the power of n. And we would probably want to rewrite this again, kind of separating the negative from the x. So how about negative 1 to the n, x to the 7n? And we're going to antiderive that, okay? Remember that to antiderive, all you have to do is add 1 to the power. So x to the 7n plus 1 divided by 7n plus 1 plus c. That's it.